good now?
Yes.
All right. Thanks. It's actually indeed my great pleasure to be here. The title of my talk might be a bit weird because you see like three terms over here, and probably none of the three is used. It's like most commonly known rule over here. But let's see. Let's find out whether we can resolve this potential kind of surprise. So every presentation is actually a personal story. Mine is as well. And let me give some background. So I've always been a computer scientist from bachelor's to the end of my PhD and even later. And I've always been interested in philosophy, and Kant was my, let's say, favorite philosopher. And I found out why it was the case quite late, maybe when I was like 40 years old or so. And kind of that has kind of that kind of moment of consciousness helped me find out. So the primary research question I'm interested in, and the presentation will be about my first fully fleshed out answer to that question. I mean, that's the best I was able to do. Okay, let's make a thought experiment. I don't know if you heard of like 𝐓𝐢𝐭𝐫𝐚𝐜𝐭. In Turkey, I think his most famous book is The Metaphysics of Love, but he has much more than that actually. He has a very famous phrase, so it's in German, whatever it's written over there. So that phrase has been written in 1839. Let's make the following thought experiment. What would happen if Arthur Schopenhauer lived today? So he's resurrected yesterday. But he's kind of project his background to the current background, and he became aware of AI and all that, and neuroscience. What kind of a phrase he would say? So the original German version actually says, one can indeed do what he or she wants. Actually, it says he. Such things were not so sensitive at the time. But he or she cannot want what she wants. So there is kind of an important catch over here. So his intention is actually to to make some points about free will and all that. Actually, but the intuition comes from the quite active research going on in neuroscience nowadays about the functional areas in the brain. So one can do what he or she wants. Actually, points to the motor cortex. That's kind of at the top of the brain. From the motor cortex is the place where kind of emotions are planned, like long-term emotions are planned. I want to kind of grab this bottle. So the moment I decide, and before I kind of get to action, so at that moment, that action pattern is planned in the motor cortex. So that's the one can indeed do what he or she wants part, and in reinforcement learning lingo, it's the pulse, control pulse. And probably Schopenhauer will be aware of reinforcement learning. He was a hardworking person, and but cannot want what he or she wants. What does it really mean? So we have, we attribute all human-like, features to our prefrontal cortex. That's the primary part. That's a lot different from the other types of animals. But you know what? So that's only a computer. So it is, so to speak, a computer program. But who is the user? So the user is the limbic system, basal ganglia, and it works based on like dopamine reward. And that's the orchestrator of the whole system. I think that's what he was referring to, or he was kind of sensing without knowing. But he wouldn't stop over there. Probably he would be aware of cognitive neuroscience at a larger scale. There is also kind of a perception part of the game. And he was completely silent about that. And my presentation will be about the computational aspects, or like the aspects of the following facts and their projections to computer science. One can also perceive what or she wants. If I really want to perceive something, I perceive that. If I want to feel pain, I will feel pain. But I won't be able to want what I want. Let's not forget that. But we are not able to perceive without predicting. So the human brain is a prediction machine. Without predicting, we cannot perceive. Also, that's how the hardware is working. Have you been aware of quantum limb phenomenon? So people like sometimes people lose their limbs in accidents or so.
Quantum field, right?
Quantum limb, like it has different aspects. So suppose you don't have an arm anymore after 20 years or so. There's a long period when you have the illusion that you have an arm.
Yeah, it's also like quantum pain in a game.
But also there is nowadays quantum phone buzz phenomenon. I'm actually having that. I don't know you. Oh, is my phone ringing? No. 5 minutes later, again, it's the predicting brain. The brain always does prediction. Without predictions, perception is not possible at all. And predictions are made for action, to take actions. Action and perception is a loop, and everything is connected. Action, perception, and control policy. Let's see. What is the math behind that? It has always been a big question, at least like for 200 years or so. So you see the regions of the brain over there. I won't pretend that I'm a neuroscientist. Definitely I'm not. But I can point you to a kind of an interesting fact over here. So the occipital cortex you see over there, it's where kind of yes.
Sorry, what do you mean by prediction here?
So like some part of the brain, let's say, makes some computation and it compares, the result of the same computation based on some stimulus, and it takes a difference, and based on that difference, it updates something. Does it make sense? So there is a region in the brain, let's say, it encodes kind of a certain object. It encodes when a certain type of input is received. It is associated with a certain type of object, let's say. And it first makes a prediction that there's an object over there, or there will be an object over there in the next sensation moment. And then it compares that prediction with the result of the perception. Was I able to at least give a partial answer? Or maybe you're asking like how come in the brain data, like raw brain data, we are seeing that? That goes.
So it's the prediction of what will be perceived
Yes.
next
Yes.
with what's actually perceived.
Exactly.
Okay.
Try and make it call once again.
Should I stop? Or?
You can share your screen again.
Yes. So, like occipital cortex is linked to let's say the sensory input. That's why it doesn't depend on anything, but all the else, so all the rest of the components are connected in a forward direction to each other, except striatum and BTA/SN in the middle. That's where the basal ganglia is. Probably because I'm not a neuroscientist, I have no clue how this is generating its signals. But at least I did my best and I couldn't find out how come that part of the brain is determining what to do. That's actually why the rewards are generated. And what's really interesting in that is that rewards that are perceived and the rewards that are predicted are generated at the same part of the brain. This basal ganglia. So it's like let's say I predict a good moment that will happen 5 minutes later. That kind of releases dopamine. That good moment is, let's say, kind of the moment where I will eat the chocolate. And that dopamine is created in the same place in the brain where the dopamine is created after actually eating the chocolate. Reward generator and the value generator is the same place in the brain. And that's also where temporal differences are calculated. I make a prediction about how much pleasure I will, let's say, I will perceive. And I do the same, I don't know, two seconds later, And I compare what happened in the like elapsed 2 seconds, and these two comparisons should match each other. That's what temporal differences is, and that's actually the essential thing. So that's kind of the essence of how, let's say, locomotor organisms can make like long-term plans. That's also the essence of reinforcement learning. Now the big questions. There's an information flow over here, so we want to model this information flow and like learn something about it in doing like in building highly adaptive AI agents. What is actually the information that's flowing? And what's the purpose of this flow? Nature doesn't have a purpose if we kind of start from this standpoint. So we need to use like optimal control terms. It's a 𝐓𝐢𝐭𝐥𝐞 function where the system will stabilize. Which equations govern this flow? And how come this flow, kind of whatever information, whatever passing is happening, how come does the agent adapt to this environment? Adaptation is a kind of an emergent thing. How does it come to play? So the answer is something like unconscious inference. So there is kind of some hidden representation, let's say latent embedding that's calculated by the brain, like as a result of some stimulus. That's how 𝐀𝐻𝐿𝐭𝐫𝐚𝐜 started. Then we have predictive coding. So we make like the brain makes a prediction and compares that prediction with the perceived stimulus. No, so 𝐀𝐻𝐿 and Pouget says it's not enough. The brain also does a Bayesian calculation. So stimuli are likelihoods. So there's always been kind of prior belief that they're updated with these stimuli. And there comes like Carl Friston. He says, no, I connect, like I close the loop. We have only been talking about like perceptions until now. How about actions? Both actions and perceptions follow a single training objective. I found what the 𝐓𝐢𝐭𝐥𝐞 function is. It is some specific type of variation inference. That's what I will show you. So I will make it quite similar presentation in 2 weeks to Carl Friston's students. So I don't know whether they will actually or like me. I will report to you. Predictive coding. So let's kind of see the math of cognition then. We are talking about the like whole brain scale modeling, right? So I mean, in the individual neuron level, we have kind of a different set of let's say equations that have been derived. So we have an agent. The agent has a word model. The word model comprises 3 key elements. First, let's say sensory input X and latent representations of the sensory input Y and S. Why do we have 2 different types? So S is kind of the part of the outside world that are outside our affordances. So that's the part of the environment that I cannot do anything about. And Y is the latent representation that I can intervene in. Then let's say first, actually the predictive coding people suggested that so there should be kind of an evidence lower bound that's maximized. So it is just the same machinery as you would use in building a variation autoencoder, let's say. So I won't show the derivation. So the goal is kind of the maximize the model fit by choosing the, let's say, right posterior distribution on Y and S. But it is a specific type of elbow. I mean, for it to be predictive coding. So the prior distribution you see, like P0YS, let's see if I can use my, no, I can't use my pointer. So Pi0YS, that's a kind of prior guess on the latent representation. So that prior guess needs to follow a certain form. That form is the horrible thing you see kind of below it. So it's a probability density function. That's why like small f of the prior. And the premise is that so the probability density function of the prior should be proportional to the expected stimulus, where the expectation is actually the expected elbow calculated with respect to the stimulus, where the expectation is taken with respect to the word model. So I simulate forward in time using whatever word model I have, and I create, so to speak, like data from this word model, and I evaluate this synthetic data on my own word model, and I will take actions that will fit my word model. I have 2 options. If it doesn't work, either I will update my policy or I will update my word model. That's how action perception loop is kind of completed. Yeah. Yes. Am I missing anything? So we have a do operator over there. So this two operator is using the causal inference lingo. So we are intervening into the distribution of the word model Y, kind of calculating this 𝐬𝐭𝐿 function. Good. So what's going on actually in this prior calculation is quite similar to the weight-sleep part of deep generative networks, if you have come across that. So you train like deep generative networks on real data, and at some moment you stop, and then you kind of try, let's say, start another process. Jeffrey Hinton was talking a lot about that. So where kind of you generate synthetic data from your own, let's say, from your inferred world model, and then you keep fitting your world model on your generated data, kind of, to make it consistent. His also claim is that so what's happening in the brain while we are sleeping is something similar to that. That's what it's called. Okay, active inference is not yet this. It is predictive coding. Characteristic says actually we are missing in this missing reward in this feature. We need to add reward somewhere. So what's the basal ganglia doing? It's generating reward. So the world model is the joint distribution x, y, z. So the first part of the equation over here, like the one you see in the middle, is the most obvious outcome of like the product rule. But what we can do is that we can kind of flip around this product rule and kind of decompose the two variables in a different way and isolate the part that's related only to the stimulus. And this part is only theory now. I don't think our person has observed this in the brain, but apparently it's working well. It's fitting well to data at different scales. So the basal ganglia is like intervening into this p tilde x. So what kind of stimuli are preferable? Sometimes he calls this like the bias distribution or desired state distribution, which states I want to perceive. So that's generated by basal ganglia, what I want to perceive. That distribution over there is kind of, we apply a do operator over there, like into that. So the one you see, I mean, that's the best thing I can do. So x tilde PR. So there we are doing the intervention. And I mean, I use this intervened word model. So intervened into, like after the intervention takes place into the isolated desired state distribution, I calculate the prior I have shown before. I plug everything into the elbow, and I come up with yet another even more horrible, equation you see at the bottom of the slide. So what do we have realized as a kind of side result in the recent paper we have submitted? So this like a consequence of applying this do operator and also intervening into the prior distribution and replacing it with the posterior, that's what you need to do to apply this weight-sleep scheme. Actually, effectively, we are disconnecting the latent representations and the stimuli. This means we don't need to learn the posterior PYS given X, because PYS given X equals to PYS. And I can read it out from my model alternative. I was shocked to see this because the whole active inference field is actually struggling to approximate this distribution. And we found out that, so if we do the math like rigorously, following whatever Patrice is saying, but sticking to logical consistency, that's it. We come up with something that kind of actually completely, bypasses the main computational difficulty he came up with. And we even tried to implement this posterior distribution by Laplace approximation or so. And my student was reporting to me, but I mean, this outcome, whatever kind of quantity we are having over here, we have a mirror of it as another term in the loss function. It cannot be an accident or so. I mean, we are looking into, so the equation is correct. So how can it happen and so on? Then we realize that actually these kind of two parts of the system, they are disconnected and they have to be disconnected. And we have proven it and we put it into the active inference is actually much simpler than how it looks. So this horrible equation, what do we have over here? So the policy distribution, PA, an encoder, and a latent state transition distribution. So we first project ourselves to the latent space, and then we kind of apply our transition model to get to the next state. And then we apply a decoder and we come back to the the stimulus space. I will not get to the details of this equation, but this autoencoding part will be important later. Okay, the problems of active inference do not stop here. So it was so nice of Carl Friston to introduce the role of reward into the predictive coding formula, and thanks, he made it like even more complicated. But remember what I said. So reward generation and expected reward generation is happening in the same part of the brain. How about expected reward? He only talks about immediate reward. But the essence of adaptation, like long-term adaptation, and actually where we are using our prefrontal cortex is to make that kind of long-term plans. And the temporal differences aspect is completely out of the game. So like the best thing we can do from this formula is to use it. I don't know if there are any mechanical engineers here. So model predictive control. So we kind of fast forward, let's say we make a prediction for multiple time steps. Suppose we have a simulator, we always simulate and we find the best trajectory among simulated, let's say, potential futures. Okay. Do I have a kind of phantom?
No,
Okay.
okay.
It was not a phantom audio. Okay. And the role of temporal differences have been missing until now. It doesn't say anything about the planning horizon for how, okay, we want to temporal difference learning. Then at least tell me like for how many time steps I should go. The theory doesn't say anything about that. And how come, like based on which principles should I do state abstractions? Meaning how, like based on which principles should I go from the state of stimuli to the latent space? And I don't know, more daily lingo from stimuli to constants. The theory, I mean, it's supposed to be the theory of like math of cognition, but it doesn't say about the most essential aspects of cognition. And okay, well, but why should we care about these three missing things? We are computer scientists, after all. We don't know how to extend active inference to Bellman backups. This means kind of all our roads are blocked if we want to learn something from neuroscience and apply into artificial intelligence. Second, if we are working on like high-dimensional inputs, like what technology is doing, like autonomous driving or visual control, we need to kind of do state abstractions, and active inference just throws over the fence the concept of state abstractions without saying how exactly we should, treat that one. The actionable consequences. Active inference has been tried in reinforcement learning. Let me tell you what happened. So people ended up with doing model-based reinforcement learning, something like Dreamer, and just looking at kind of Dreamer components, they were able to say, okay, after this Dreamer component corresponds to kind of this outcome of active inference. Its role was kind of justifying ad hoc loss functions with findings from neuroscience. We have a more ambitious program already. So we want to do the math in such a way that this is how cognition has to be taking place in the brain. We will kind of project it to the AI area following kind of taking the deductive steps. Good. Any questions thus far?
What's wrong with Dreamer exactly?
Hmm?
So the problem is adapting Dreamer to active inference, right? Not the Dreamer itself.
Actually, they are not even doing that. They are just looking at the individual terms of Dreamer, and they are saying, okay, this term of Dreamer probably works because the brain is also working that way.
Oh.
That's it. So its role is justification, not like really learning something and transferring information from cognitive neuroscience into our reinforcement learning. So probably, I mean, in sparse reward reinforcement learning also, there are people generate like intrinsic reward. So when reward is very sparse, you need to make up your reward yourself, right? There are reward types like info gain and so on. They are also justified by activities. Good. So active inference is not active learning. It's something else. It's not only inference, it's a specific type of Bayesian inference, which also contains actions. Short. We will get to the distributional part. It has some relation to distributions, but probably not the first thing that comes to your mind, unless you have done the precise distributional reinforcement learning thing before.
So what does the last sentence mean? It doesn't help more than justifying cases. It's just
So like,
So it is like using the reinforcement learning to justify what you have learned. Or
vice
what-
versa. Reinforcement learning justifies its ad hoc solutions by hand. But they are existing solutions. So it's kind of like ad hoc generated loss functions, post hoc justified by learning something about that. It's not derived from it. Good. Our ambition, make a genuine reinforcement learning algorithm from active inference. What do we count a solution, a good solution? So what are our expectations? Incorporate temporal differences into the theory so that we can come up with an agent that can also plan an infinite horizon future. So I want to determine my next action based on a precise calculation that goes until the end of my expected time. Because computers have like enable us to do that. And clarify the role of state abstractions. How much state abstraction we should do? How exactly state abstractions help an algorithm to learn something better or faster? And what's the role of uncertainty and how it comes together with state abstractions? Quantify this and also explain. Okay. Now a little more boring, but the manual part will start. So we will need to get like distributional reinforcement learning, active inference, and actually model-based reinforcement learning and put them together. And all of the three will be outside their comfort zone. That's why, sorry for the complications that might be generated. So reinforcement learning is actually built on dynamic programming. And dynamic programming has three, let's say, canonical algorithms. I don't know, fourth one actually. And all the reinforcement learning algorithms are noisy versions of these idealized algorithms. One is value iteration, the other is policy iteration, and the third is linear programming. Linear programming is out of the game, it's too expensive for this context. And we have chosen like policy iteration because, because of some technical reasons, we need to kind of dissect the part where policy evaluation is done from the policy improvement done. And we kind of extended it to the case where the Bellman operator, the one you see kind of at the bottom, that's the operator that calculates the temporal differences, that kind of fast forward us to 1 time step further. So we have written it down first, making its dependency on the state transition probabilities explicit. Typically, you write it as like T, like the transitional, like the operator T, and superscript pi, and that's it. Then you evaluate it with a certain function Q. We specify that we are evaluating the Bellman operator with respect to a specific transition kernel. And that transition kernel is actually the one you see as like in the policy evaluation part for to do a Bellman update. And this Bellman update is done differently from standard policy iteration after a model update where some maximum likelihood estimation, whatever is used, on the actual observations. Actual observations are obtained from the kind of true transition kernel P star. So we extended the policy iteration algorithm to the model-based reinforcement learning case. It's still idealized. We still assume that we have access to the we are able to calculate all the expectations over here exactly and so on. It's not the case in standard reinforcement learning. And we will kind of stepwise modify this algorithm. That will bring us like build the bridge from model-based reinforcement learning up to distributional. How about distributional reinforcement learning? What's special with that? If you have done any reinforcement learning, you might have heard of something called a value function or an action value function. It is defined as the expected sum of rewards starting from a certain state or state action combination. I'm at a certain state. If I take a certain action and follow a certain policy until infinity afterwards, what is the expected sum of rewards I will? All based, let's say, standard reinforcement learning machinery built on the assumption that so the value function is calculated for the expectations. What if I want to take into account uncertainties? What if I'm interested in the distribution of the function? I'm not satisfied with the with only the expectation over here. I want to calculate the whole distribution. It's kind of the fast track. So using distributional reinforcement learning, we will bypass the need to develop a word model. There will be an underlying word model, but we will never explicitly have. So we will have something modeled. Although there is always an implied transition curve in mind. So the difficulty of distributional reinforcement learning is the following. I mean, when I first started to do reinforcement learning with like with a probabilistic standpoint, so I saw this expectation over here. I thought, why not add a variance? Then let me model mean and variance. I can do some amortization and so on. You know, it doesn't work. Let me tell you why. So the return distribution looks as follows. So we have a certain return distribution for the next time step, and now I will apply Bellman backup on this. I apply the reward function, which shifts this distribution. So it's kind of the whole mass shifts, and now I apply the discount factor. So I just scale it. I make it a bit more kind of compact. And voila, so there's a mix over here. So I need to take the expectation of the return distribution. No chance you will generate a very multimodal distribution. Even for like extremely simple systems like two-state systems with only binary reward or something, it doesn't matter. So the return distribution will be super complex. So we need to do like non-parametric modeling, and people typically use in this case, quantile regression and build those tools. So then still the challenge we need to solve or face is that so we want to assume a world model, so which is a state transition distribution. And we need to put it into the distribution RL framework in such a way that we can calculate its algo and so on. How can we do that? So the way we came up with is to kind of model the return distribution as a combination of two things. One is something we call Markov process measure, meaning what is the probability of an infinitely long trajectory in a certain dynamical system. It goes until infinity. I will never calculate that trajectory, but it's enough if I just do the math. So first I need to make sure that such a probability measure exists. That's not something we so much care about in daily life, because whenever you see a random variable, you directly use it, right? So it has an expectation, so. In probability theory, things are not as simple. There's something called an underlying measure. I don't know if you heard that. A random variable is built on top of an underlying measure. And they are not necessarily the same. And here we had to kind of get back to the measure theory and calculate things at that scale. And we came up with, whether the details are not so important, but a Markov process measure, it's kind of, let's say, probability distribution that assigns probabilities to infinite long trajectories. Okay? Trajectories of perceptions. And we defined a functional which is also infinite long. And we put together these two things and came up with the return distribution. Infinite long function applied to infinite long trajectories gives us the return. So I talked to distributional RL guys, and they verified that. So their distributional reinforcement learning book doesn't cover this one. So I exchanged emails with what was the guy, Mark Denmark. Probably do the qualities. Anyway, so we call this a push forward Markov process. Push forward measure is the thing you do on top of the base measure to calculate random variables. The medias are most important. So the return distribution is a composition of a Markov process measure and kind of an infinite long function. Then how can we do reinforcement learning using that? We need to come up with an operator, and then we need to show that this operator is a contraction mapping. So that's why reinforcement learning is working. So if you are using reinforcement learning in its comfort zone, things work, you don't need to worry about these contraction mappings and so on. But if you want to change something at the fundamentals, then you need to make sure that things will converge and the theory is still in order and so on. That's why we had to analyze its contraction properties. we came up with a distributional variant, or let's say functional variant of the Bellman operator. It always operates on like infinite long sequences now. And we were able to show that it's actually a contraction mapping. It's an extension of Bellman's number. Just which word model I'm assuming is made explicit. So it's kind of, I choose two different word models. One is P and the one is P bar. So if I apply the same push forward in both, and if I apply a Bellman operator afterwards, I know that, so the outcome will kind of get similar to each other than before. This means if I keep applying Bellman operator, that will be a fixed point. Convergence will all. What kind of key implications does this kind of horribly boring math have? Actually, it has quite many operational outcomes. There is a fixed point, fine, but the fixed point is with respect to the push forward functional. It's not with respect to the word model, meaning there doesn't exist a single word model that explains a sequence of rewards. That also explains how, as humans, we can survive without developing very accurate physical models. Because there's a very big equivalence class over there. So what matters is whether the push forward of my word model after a certain reward function generated by basal ganglia makes any change in the policy I'm learning. If not, who cares? Just learn a wrong word model. Otherwise, the problem is just too complex. You won't be able to learn it. Just try to do model-based reinforcement learning. You will understand what I'm saying. Just plan like 50 time steps, not 50, 5 time steps ahead and try to kind of do reinforcement learning. It won't work. No way. So I'm sure the brain is not doing that. So I'm sure I'm not doing that. So why things are simpler? Because we are operating on push forwards, which generate big equivalence classes. Okay. Then we had to do some further, rigorous math on in which cases state abstractions may be useful, might be useful. I really don't want to get to the details over here. We had to define a notion called like Lipschitz Markov kernel, a Markov kernel that behaves like well, smooth, and so on, and the kernel operator that puts together like a kernel and a kind of continuous function, and this combination is then put into our push forward functional. Long story short, we came up with another proof that actually has like two terms over here, LE and LD. It is the Lipschitz continuity of the encoder and Lipschitz continuity of the decoder. This proof shows that if your decoder has small Lipschitz continuity, then your system will converge faster. Meaning, if you can go from the stimuli to an underlying latent embedding, where the upcoming rewards really start not to matter so much, but like with respect to which element of an equivalence class you are within, then updating your actions based on this word model will make you converge faster. The larger equivalence classes you generate, the faster you converge, meaning the better concepts you develop that cover kind of certain phenomena, the better survival chance you have. That's actually where science is evolving as well, right? So we have sharper concepts that describe, like better defined concepts that describe more things. With less words, we explain more compared to before. And that's the motto, at least in my view. So this is called like combined, these three guys. I mean, whatever you see over here is called in reinforcement learning literature the contraction modulus, and it determines how fast the system will converge. So by applying an autoencoder, you have the chance to put kind of two coefficients over here. And because you are in charge of developing your own word model, you can come up with such a word model that at least one of the two Lipschitz continuities over here have kind of are small. They are less dependent on inputs, let's say, then the system will converge faster. Let's visualize the things. This is a quite iconic example for theoretical reinforcement learning. We have a river that has flow on the left side, and I start from the first point of the river, and I get a very small reward. I stay at S1. It is, so to speak, my comfort zone. So I want to start making sports, but I mean, I want to lie on the couch, etc. If I kind of take 5 steps ahead and get to state S6 without taking any rewards in the middle, I will reach at kind of a state where the reward is 200 times higher. Whether such a system can be solved, that's a lot to the reinforcement learning coefficients. Whether your agents can learn delayed rules. What we did was the following, and because reinforcement learners were not so busy with like the autoencoder aspect of the things, we tried to put this reverse swim to the latent embedding of a system, and we applied a very simple autoencoder. So you just take the average of the coordinates of a kind of two-dimensional system. Yeah. And as you see, as the horizon grows, equivalence classes also grow. Yeah. So state 0 corresponds to 3 states over here. State 5 corresponds to, I don't know, 10 states 2, sorry, corresponds to like 10 or more states in the observation space, and so on. The longer the horizon goes, the bigger the equivalence classes. Okay, and I will pass over this part a bit fast. So we put together our push forward functional with this composite kernel thing I have just shown, and came up with, did some calculations and came up with a scheme which actually boils down to performing distributional reinforcement learning on the latencies. And the interesting math has shown us, using actually some tricks that we learned from Wasserstein autoencoders that are completely unrelated to our research actually. That's what's like deep generative networks people know better. We came up with an algorithm where it is enough if you map your current state and action to a latent state, and you don't need to really learn kind of state transition kernel at latent state. You can just eliminate that, and then you can assume that from that latent state on, the processes run until infinity. Then let's do kind of model-based reinforcement learning, model-free reinforcement learning on that ground. And we came up with a new algorithm called push-forward policy iteration. It is kind of an extension of distributional reinforcement learning to the latent spaces I have shown. And then we used, and then we put the pieces together in a particular way. And we made some observations about how the terms in the L will look and so on. And we have proven that active inference is actually a push-forward policy iteration instance. It can be cast as kind of a special case of this more generic algorithm. And we have implemented it. And it boils down to extending quantile regression to its maximum likelihood estimate counterpart, and then do some amortization on its sufficient statistics and so on. Not really so important stuff, and we came up with an algorithm. Believe it or not, it's really not so difficult to implement. It's simpler than we. So just it's written in a mathematical lingo now. Then remember the reverse swim. Okay, the boring part is over, so we can relax. I will just figure this out. We first try to do like a proof of principle. If this is how active inference is working, then let's kind of determine 2 cases where active inference should be useful, and another case where it is not useful. And is it really what we see? Indeed it is. When we do reverse swim, meaning reinforcement learning without a latent space, without doing an active inference at all, TSR-LPI is a model-based reinforcement learning algorithm. It is much better than us. Not surprising, because we are learning autoencoder, it's not. But when the reverse swim is latent, when there is a need to do active inference, then model-based reinforcement learning, and actually in tabular MDPs, let's say in theoretical reinforcement learning, TSR-LPI is like the golden child. So it's kind of an unbeatable algorithm. It just collapses extremely fast as the reward starts to delay. Like plain distributional reinforcement learning, whatever Belmar has invented, is never so good. And our active inference supported distribution version just doesn't mind how far you go. It can just plan ahead, go along. Its performance is just this, not disturbed. I was so happy to see this. So the theory is working. Then we took another step. So I mean, let's challenge our hypothesis even more. Let's try to beat each algorithm developed for its own application area and its own realms, but with a single algorithm without any fine-tuning, anything. 𝐓𝐢𝐭𝐥𝐞, it's that soft robotics application, so the robot itself kind of defaults. It's much more difficult to kind of manipulate. And DMC dog run, so DeepMind control suites, I think most difficult locomotor. It is typically the iconic example. We are still not able to run our algorithm on DMC dog and so on. And we also tested it on like visual control. So you are trying to kind of run this quadruped thing by just pixels. So there is a pressing need to kind of project the things to a kind of low dimension manifold. And 𝐓𝐢𝐭𝐫3 is actually the best working algorithm in DMC vision. We also compared it to Dreamer, by the way. We are better than both. On DMC vision, better than DSAC and so on, all the distributional variants, and also the standard reinforcement term. They are completely out of game, by the way. In DOC, and the same in 𝐓𝐢𝐭𝐥𝐞. I mean, these are kind of selected environments, but in total, we tested our algorithm on 17, 18 something environments. Actually, that's pretty much it I want to talk about. Let me just give a glimpse of what we are working with. So how we will take the things from here. We still haven't done a proper like finite sample analysis. We want to forecast for how long our agent needs to be in training mode to reach a certain performance. We want to do some pack analysis of it. How can we do multi-objective distributional reinforcement learning? So, and how can we learn a kind of something like a Pareto prompt? For instance, we want to come up with a robot that maximizes the reward in terms of kind of solving the manipulation task while consuming minimum energy, while being environment friendly, however many criteria you want to define. Of course, you can always take the sum of them and make a composite reward, but typically it's better to do multi-objective reinforcement learning where you learn a Pareto prompt, and then later on, post-hoc, you can choose like fine-tune where you want to step. It can be done post-hoc without needing to kind of run your algorithm up there. Measure theoretic RL, that's something that has an interesting story. I started to like writing new lecture notes for my reinforcement learning students, and I ended up with writing a paper. We tried to kind of put the whole reinforcement learning complete measure theoretic terms nowadays. I mean, if it becomes successful, then hopefully there will be an archive written by the Europe's deadline. And we also want to learn like foundation posts using kind of quite similar tricks, meaning we have big offline data and we learn such an essential information from such offline data that whichever reward function you give to them later on, the test time, I just make an algebraic calculation and then give you the optimal false. That's actually possible. I mean, there's more code cases it has been kind of tested before. We are trying to kind of put it into the extremes. Okay, if there has been anything that has interested you, it is due mainly to the hard work of my colleagues. You see over here. So the first QR code is linked to our lab website if you're interested to see our other papers. And we have a code repo called 𝐓𝐢𝐭𝐥𝐞, which is tailored specifically for people who are not properly in reinforcement learning, and it's been written in like sticking to object-oriented programming principles, so that like all the basic components are turned into classes, methods, and derived from each other or so. And it's been tested mainly by one of my postdocs who comes from a completely different, like non-computer science background. He was able to learn it quite fast. He's coming from finance background, by the way. He's an economist. And it gave me kind of good belief that as computer scientists, I mean, it shouldn't be so difficult to do this. That's it. That's all I have. Thanks for being patient with a potentially complicated storyline, and I'm happy to hear your questions.